Welcome to lecture 25 of PDEs. During this lecture, we'll continue looking at the Sturm Liouville Theorem. In particular, we'll be looking at the properties of the zeros, the dependence on the parameter or the eigenvalue lambda, and finally the proof of existence of an independent set of basis functions with an infinite series of lambdas stretching from 0 to infinity. And we'll also be looking at, in the second part, we'll be looking at how to expand a function on the eigenfunctions basis for a particular Sturm Liouville problem. Okay, so the Sturm Liouville theorem we've been looking at to date basically is a theorem associated with the operator L, where you have arbitrary functions px, qx, and wx, and they obey certain properties. P and w are greater than 0, and pp prime qw are continuous on the interval ab, where you want to solve the problem. Last lecture we sort of looked just at features of solutions to this operator. What we're going to do this lecture is look at the eigenvalue problem. So we're going to define the eigenvalue problem to be the operator applied to y plus lambda, which is a constant to be determined, multiplying y is equals to 0, and we're also going to look at separated boundary conditions, okay, which is basically specifying this condition at the point A as well as at a point B. In the last lecture, we looked at the properties of this operator equals to 0, but we looked at them where we had initial conditions simply specified at A. Okay, where we specified as in normal, any ordinary second order ODE, you would have to specify both the function and its first derivative. We did that and we looked at the properties, and the way we did it was to make a very clever pre-first substitution which permitted us to, which is basically u is equals to r sine theta and pu prime is equals to r cos theta, and that allowed us to separate the second order differential equation into two first order equations, one of which is the equation for theta that decouples. So that permits us then to solve or explore the properties of theta, which is now a 1D ODE with boundary conditions that we know only one of them, and then find that solution and then put it back into the differential equation for R, okay, and this right hand side is entirely determined if we know what theta is as a function of x, and then we have u immediately from there. Okay, and we related the initial conditions to the initial conditions we specified for u in the following manner. Okay, so what we're going to do now is go back to the original Sturm Liouville problem that we have to solve, where our boundary conditions are no longer just being specified at A, but at both of them. But we're going to use, because of this nice substitution, we can actually use the results from lecture 24 to derive what we're interested in looking at for the Sturm Liouville theorem. So let's go about seeing how we find the relation between the eigenvalue problem with separated boundary conditions to the ordinary ODE problem, second order ODE problem, using the pre-first substitution with boundary conditions just at A. Okay, so the first thing to note is that the Sturm Liouville eigenvalue problem can be simply recast as a problem like this, but with a different linear operator. Okay, and in fact, the new linear operator has exactly the same structure as the one defined L. We just have to redefine what the functions p and q are that we use. And then we do that as we basically say p tilde is simply p, w tilde is simply w. So if p and w are greater than 0, the tilde versions inherit that. But the thing that we change a bit is q. We say q tilde is now q, the function we defined the operator L, plus lambda times w of x. So it's still, if q obeys all these properties over here, q tilde also obeys all these properties. So we've just simply recast our eigenvalue problem as a ordinary problem that we've solved in lecture 24, but just with a slightly modified operator. Okay, and the boundary conditions at A are actually surprisingly easy also to put into the form that we used the last time. In fact, if you have noticed that the boundary conditions over here entirely determines theta 0. In other words, even though we haven't specified two boundary conditions, the one that we have specified permits us to work out theta 0, which is the initial condition for the theta equation. So we can still completely solve the theta differential equations just from theta 0. So here we have tan theta 0 is simply equals to this ratio of constants that we use to specify our separated boundary conditions plus P of A. And then what we then have is the pre-first substitution is simply this thing where we've replaced our normal definition that we derived over here just with a modified Q. And this is the equation we're now going to exploring, at least initially. Okay, so the first thing we're going to do is explore this equation's dependence on lambda. Okay, and the statement is, or what we're going to prove is, and I'm going to illustrate it in an example on the next slide as well, is that the solution theta tilde of x and lambda is a continuous monotonically increasing function of lambda. And of that, lambda is important because remember last time I gave you an example where theta tilde of x need not necessarily be monotonically increasing, although it had that ratchet property, so that once it had passed the value of theta equals to n pi, it never fell below that, although it was not monotonically increasing. However, if you consider it to be a function of lambda, we're going to show that it is strictly monotonic increasing as a function of lambda, and that is true for all x. Okay, so the proof that we're going to use is simply to use the comparison theorem that we explored the previous time, and we're going to choose an appropriate comparison equation that is actually very, very close to the equation for theta tilde. In fact, we're going to choose a comparison equation in which only our q has been modified. So instead of having q tilde, so we see here p hat is p, which is p tilde, but q hat is lambda hat w plus q. Okay, and this lambda for at least for our case here is going to be assumed to be different from the lambda used for this equation over here. Okay, and also note that we're going to use the same initial condition. So theta hat or theta 0 hat is going to be same as theta 0 tilde, and they're both going to be assumed to satisfy the separated boundary condition at A. So now where it comes in and to show that this is monotonically increasing, we're going to say if lambda is greater than lambda hat, okay, then we have q tilde is greater than q hat on AB. And if you remember, there was a theorem in lecture 23, I called it P3, that then stated this was the case where we had the strong inequality on Q. It also this was enough to imply that theta tilde is strictly greater than theta hat, okay, on all of x, okay, provided we've chosen the lambda greater than lambda hat. But if you look at the definition up here, theta hat of x lambda hat is merely theta tilde of x lambda tilde, okay, from which this result follows. Okay, and this is true for all x greater than a, so theta tilde lambda is a strictly increasing function of lambda. Right, so this is necessary because we're going to start exploring how we tweak lambda to satisfy the second boundary condition, and how it is possible to always satisfy it, and in fact to satisfy it for a whole series of functions. And we're going to label those functions with the lambda we used to satisfy them. So let's now, just to get ourselves exercised, let's look at Matei's differential equation. Remember, we derived it when we separated variables on the elliptic membrane. And there, it's basically, I've just renamed the constants to put it in its sort of standardly explored form. We basically have y second derivative is equals to lambda, which was associated with the separated constants in the way that we were derived it when we were looking at the membrane, minus 2 epsilon cos 2x y. And y is considered to be a function of x, and x is being explored in the domain from 0 to 2 pi. Okay, and we also want periodic boundary conditions because that's the physical situation we're in with exploring it on the membrane. Remember, it was for the C2 variable, which basically said that you had to identify 0 and 2 pi. So we're going to say, look at the condition where our periodic boundary conditions, we basically have that y at 0 is equals to y at 2 pi, and that's equals to yp. And y prime at 0 is equals to y prime at 2 pi, that's yp. So both the function and its derivative are continuous as you identify 0 with 2 pi. Okay, so this then gives us the initial condition, theta 0, and in fact it also gives us the relation for the boundary conditions at 2 pi. But for now, let's just consider the fact that from the A point we know what our initial condition is, and that's tan of theta 0, or theta 0. Okay, and now we're going to solve the Prefer equation for theta, and that just becomes, because p is equals to 1, right? It's not, there's no coefficient multiplying the first derivative of y. Remember I said be very, very careful when you look at the second order equations. Any second order equation can be placed in the Sturm Liouville form, but you have to work with them in that form. And here, this thing is actually in the Sturm Liouville form with p is equals to 1. Okay, so we have cos squared theta plus sine squared, and here we have theta multiplied by the contribution from q. So we now want to explore the solution to this equation. And I've plotted it for several lambdas. So have a look at what happens here. So firstly, lambda equals to, close to 0 is down here below. So it is possible on the domain 0 to 2 pi to choose lambda small enough so that it never crosses the line pi. Okay, and that's going to be important because our first solution is that we usually want to try and solve is to find a solution where you sort of only have a one hump, where you have no zeros. In other words, when theta never crosses a line n pi. Okay, so this is an example over here. And then as we increase lambda, it goes up higher and higher. And remember, we've just proven that if lambda increases, theta of x lambda is monotonically increasing. So what that would mean visually over here is if lambda is greater, if for a line where lambda is greater than the other one, that line never goes below the other ones. For example, here lambda is equals to 8, okay, and that line is always above lambda equals to 4 over here, and always below lambda equals to 6. Well, sorry, no, this is lambda equals to 4, and this is lambda equals to 8. It's always below lambda equals to 8. Okay, and so another thing you can notice, if lambda goes to minus infinity, and this is actually a theorem we're going to prove later on, this line, you can prove that theta goes to 0. In other words, this line becomes completely flat. And if lambda goes to infinity, in other words, it gets very large, you can prove that this line becomes almost vertical. So you basically go to infinity. You sort of basically strive for infinity very, very quickly. And another thing you can observe just from these things, this line indicates where you find the first 0 of all the functions. So for lambda small, you have no zeros. As lambda increases, eventually the function has 1 0. If it increases further over here, the function has 2 zeros, basically every time it crosses this dotted line there and there. But the zeros themselves are also ordered. In other words, the first 0 of a line with greater lambda always lies to the left of the 0 of a line with smaller lambda. Okay, so there's an ordering, and as lambda increases, the zeros tend to shift more and more to x equals to a over there. Another thing that you can notice is when lambda gets large, there's a good approximation to this, to the actual shape of the function. In fact, this approximation over here I've plotted is a dotted line. It comes from the comparison equation. If you remember at the end of the last lecture, and it's an idea we're going to use again here, we used the comparison equation, which was just an ordinary sine function in terms of x in the xy plane, to actually prove that certain properties of the zeros, in fact, that you had, if the comparison function had n zeros, then you had the function you were comparing to it had n minus 1 zeros in the same interval. In fact, and that comparison function we constructed, and I'm now just going to do it for this particular example. So remember, the comparison function, we looked for constants that were the maximum to capture the extreme behavior of theta prime. And here we would construct the constants in this way. We just have p hat is equals to 1, and we would have q hat equals to lambda a minus 2 epsilon, which would be kappa. Okay, and that's basically the minimum value of this function. And what if we then do, we could then solve the theta equation, because it just has two constants in it. And if you do that, you would get this expression that kappa of tan theta is equals to tan of kappa x minus x0, which in this case is merely 0. Okay, and that is the implicit equation that is used to describe this dotted line. So you actually have a very good approximation to this dotted line. And it was in fact this solution, and we'll use it later on, that permitted us to explore the zeros, and it is the same solution that allows us to quantify the zeros, even though we have not yet explicitly solved analytically what the solutions to the Matthäus equation are. Okay, so having said that, let's start proving a number of these comments formally. So let us say, let y of x lambda be any solution to the eigenvalue problem having any initial conditions. Okay, then for n greater than or equals to 0 and sufficiently large lambda, the 0xn of lambda is defined and xn of lambda approaches a as lambda goes to infinity. So firstly, recall that the 0xn is defined as the point at which the theta function goes past n pi. So if n is equals to 1, here is the x1 of the function, and as you increase lambda, this x1 tends to move that way, and you can see the result. Eventually, as lambda goes to infinity, x1 moves to 0, which in this case is a. And the same is true for x2. Here's x2, as lambda increases, x2 moves left. Okay, and increased far enough, this graph becomes steep enough, and even x2 goes to a. Okay, etc., etc. So let's just prove that quickly. Okay, the first thing you have to prove is that xn exists for lambda large enough. Okay, and that's to basically say there's always a lambda. For example, this curve down here is an example where xn doesn't exist. Lambda is not large enough over here. So you basically have to choose lambda above above 0.2, right? At 0.2, which is this curve, your lambda is large enough for x1. So x1 always exists if lambda is greater than, I think, something like 1.8 or so, 0.18 or so. Okay, but here lambda n exists. So let's just prove that. And the way we prove it is once again to construct the comparison function, much as we constructed the comparison function here. In fact, it is this one just generalized. So the comparison equation with constant functions, we basically have p hat is equals to pm, which is the maximum value of p on the domain, and q hat is equals to wm lambda plus qm. Okay, where pm is the maximum of p, and w is the minimum of w, and we know that it's always greater than 0 because w of x is greater than 0, and qm is the minimum of q on AB. Okay, and then for a given lambda greater than 0, right, the conditions for the Sturm comparison theorem, which we did in lecture 24, which is I basically abbreviated as ACT, are valid. And the comparison equation we have is simply this thing, where kappa is now dependent on lambda, right? So kappa is just squared, is just assumed to be positive, and it's equals to lambda wm plus qm plus over pm. Okay, so there the solution becomes, we can just write down an analytic solution of this thing that has zeros, sort of as a sine function has zeros, because that's basically what it is. So we have u hat is equal to sine kappa x minus a, and we can then choose lambda so that kappa b minus a is greater than n minus 1 pi. In other words, we fit in the oscillations if we choose kappa big enough. Okay, and then if we choose it that way, you can simply plot the sine function and you can see that u hat has at least n plus 1 zeros in AB. And that is useful because the moment we use this and we apply the Sturm comparison theorem to y, we see that y of x lambda has n zeros in AB. Okay, so then we immediately, what we've basically done is we've used this dotted function, which is always less than the function we're comparing it to basically say the zeros are always bigger than that, and because the dotted function exists, you must always, the zeros for y must also exist, and there must be at least n minus 1 of them. So this we proved last time. Okay, but this is enough to say, as I've just argued, that the zeros of xn exists, of the function we're considering, and if we look at the comparison equation again, for that equation with the solution, we can basically work out where the zeros are. They're simply at x hat equals to a plus m pi over k, right? So whenever x is equals to that, you can substitute it in there, and you see that sine of m pi, because you basically cancel out the kappa, and you're left, and the a cancels out with that a, and you're left with m pi. That's 0, okay? So that's a 0. And we can also see just by simply looking at this expression that as lambda goes to infinity, right, lambda goes to infinity, kappa goes to infinity, and x hat goes to a, because as kappa goes to infinity, this thing becomes 0, and x hat goes to a. So we've formally shown that the 0 for lambda goes to infinity, the mth 0 for lambda goes to infinity approaches a. In other words, that's just as I said, as lambda goes to infinity, the steepness of this graph gets bigger and bigger, and your comparison function, which is this dotted function, gets steeper and steeper. And because you've boxed the real y tilde solution in, or theta tilde solution in, to be left of this comparison function, its zeros are also forced to x equals to a. Okay, so this I said is true for all m. In other words, it's true for this m, for x1, it's true for x2, they all get squashed there as well, and it's true for x3. Okay, so we have that, this is the boxing in I spoke about by the Sturm comparison theorem, a less than equal to xn, because xn has to be in the domain, but that is x then equals to x hat, the function you're comparing it to. In other words, this dotted function is always below the actual solution, and this is enough, this is enough to actually show that basically that the eigenvalue there goes to 0. Right, so the next thing we're going to show is simply the thing I mentioned earlier, that as lambda goes to minus infinity, this line or this function theta of x lambda becomes identically 0 if lambda goes to infinity. Theta of x lambda basically becomes infinite for every lambda that's not equals to a, for every x that's not equal, that's greater than a. Okay, so here we are. The next step we want to prove is for x greater than a, the limit of lambda goes to infinity of theta tilde of x of lambda goes to infinity, and also the limit of lambda going to minus infinity of theta of x lambda goes to 0, and that's true for any x greater than a. Okay, so the first one we're going to start with is there. We've shown for sufficiently large lambda and for any fixed n, so we're going to look at a particular 0. that the limit of the 0 as lambda goes to infinity goes to a, and therefore there exists a large lambda such that for lambda greater than the large lambda and any x greater than a, you can find a 0xn as a function of lambda that is less than x. Okay, so the statement is basically choose an x and make lambda large enough so that in some sense that sweeping fan of solutions to theta, that the nth 0 is less than x, and you can always do that from S2. Okay, and that would then imply that at x, theta of x lambda is greater than n pi, and that would hold for all your zeros, including the zeros n goes to infinity. Okay, and because you've given this explicit expression for the zeros n is equals to infinity, you basically have that theta of x lambda is greater than n pi, and n goes to infinity, so theta of x lambda must also approach infinity. Okay, so it's basically just that statement that eventually your fan goes vertical. Second part is a little bit more tricky. Okay, so we want to show if lambda goes to minus infinity, theta of x lambda goes to 0. And what we're going to do is use the prefer equation. And the way we do that is simply to say that we write it down for theta tilde. And we say if lambda is negative, okay, we're going to put an upper limit on the gradient of theta at every single point in the domain. And the way we do that is simply to sort of look at this part. Okay, so if lambda is negative, then this thing, okay, you basically have lambda is wx sine squared x theta. So you've removed the part that's associated with lambda, and then you put an upper bound on all of the rest of the part, which we say is a constant k, and it holds for all of the domain. Okay, so k is basically 1 over p of x, okay, which is basically, because it's a maximum of this thing, plus q of x, which is the maximum of q sine squared theta, because the maximum values of cos squared and sine squared is always 1. And you look at the maximum value of this thing over the whole of the x domain. So this is really an upper bound on what theta prime must be. Okay, so what we have now is that if this thing holds true, we basically can say that using also the comparison theorem is basically that theta is less than or equals to theta 0 in the initial condition plus kappa x minus a. Okay, and that is true for all lambda because lambda here is negative, right? So the maximum value of this thing is k, okay, because lambda is negative, okay? And we know that theta 0 is in 0 and pi, so it's always possible to choose an epsilon greater than 0, so that theta 0 tilde is plus 2 epsilon is less than pi, okay? Because what we're trying to prove over here is that theta tilde must go to 0. So the first thing we've got to make sure of is that theta tilde never crosses pi, because the moment it crosses pi, we have another theorem that says it stays above it. Okay, so we're looking to start our discussion. We're looking for a small bit of room, because we know that theta 0 is chosen to be less than pi. So we're going to initially start working on a little bit of space where theta in the region sort of on a plus a little bit, such that theta x lambda is less than pi, and then we're going to show we can always make lambda large enough or negative enough to keep it that way. Okay, so this is the basic idea. So basically, let there exist an epsilon greater than 0 so that theta 0 plus 2 epsilon, it's not let there does exist because we've chosen theta 0 less than pi. So that theta 0 tilde plus 2 epsilon is less than pi. Okay, and then what we're then going to say is let's set x1 equals to a plus epsilon over k. Okay, then for any value a in the region a to x1, we have this little bit of room where theta is assured to be less than pi. Okay, because we then have theta of a 1 lambda on this little domain less than equals to theta tilde plus epsilon. Okay, and the reason we have that, okay, which is less than or equals to x plus x minus epsilon. Okay, so the reason we have that is theta of a comma lambda by this thing, because we know only all that we know is lambda is equals to negative is less than theta 0 plus k x minus a. But we know that this x minus a is always, if we've chosen a1 to be in this region, is always less than epsilon over k, but we've multiplied by k, so it's plus epsilon. Okay, so that's where the first part comes from. But we can then apply it again because of the way we've chosen epsilon, that this thing is true. So we know theta plus epsilon is less than pi minus epsilon. Okay, so in this little space, from a to x1, which may be very, very tiny, we've got room where we know that theta of a lambda never crosses the line theta equals to pi. Okay, and that is true for all lambda less than 0. So we haven't yet done anything with lambda. But now we're going to do that. We're going to say, let us now choose lambda large enough, absolute value lambda large enough, lambda small enough, okay, such that we force the theta x1 lambda at x1, so at the end of this domain, to be less than epsilon. And the reason we can always do that is look here, right? If lambda is negative enough, this thing is very, very negative. Big enough negative so that it's going to cancel out the contribution of k. Okay, and that's basically we're going to construct. We're going to find the condition on lambda, basically how big we must choose lambda so that this thing is negative enough to not only cancel k, but to make sure that theta tilde at x1 becomes less than epsilon. And we once again can use the comparison theorem for that. So to see how we choose that lambda L is, let's let Wm be the minimum of Wx, okay, on x in AB, so the whole domain. And now we're going to look at the line in this tiny little space. We're going to say, let us construct a comparison function, which is just a line. And to do that, we basically have to specify the gradient of that comparison function. And we're going to have a line that joins, say, an arbitrary point A1, where we know theta is less than pi, to the point x1, which is at the end of the domain. And we're going to force it to have a value, and we're going to choose lambda L so that theta tilde has a value less than epsilon over there. Okay. So to do that, we first want to know what this M is. Okay, so the line joined with this property is basically you substitute these 2 points into the equation for the line and you solve for M and C. And if you do that, you simply get the gradient is the difference in the function values at x1 and a over the distance between x1 and a1. And you have that C is the intercept when x is equals to 0. So C is equals to that. Okay, and what we now do is we now choose the right-hand side of this big comparison function over here so that it is negative. In other words, that it has results in a gradient that is stronger or more negative than the M, which is the line that joins these 2 points. Okay, and basically the value for lambda explicitly you can calculate given the epsilon you prescribe. So you can basically make theta as small as you like, provided the epsilon is smaller than sort of this one over here, okay, than the one you know exists. So the epsilon always exists, and you can always choose it small enough. You can choose it arbitrarily small as long as it exists, as long as it is smaller than the minimum value for its existence. Okay, and it doesn't depend on L, and that's an important point. So choose your epsilon quite small or very small, and then choose your L so that lambda L is equals to this function, which we've derived from basically the M that we know in terms of epsilon and these other things, basically, which is sine at epsilon, lambda Wm, etc. And what happens then is the moment we've chosen lambda that way, okay, we can always make it small enough, okay, that theta hat of 0, in other words, that's our comparison function, 0 lambda is equals to some constant, well, it's a constant of this line, but that's greater than pi. Okay, so if you look at the line specification, we're going through theta tilde at a1 lambda, which we don't really know, except that we know it's bound. In other words, we know that we can approximate it basically with theta tilde. We know that it's less than theta 0 tilde plus epsilon, and that's less than pi minus epsilon. Okay, so we're basically going to keep making our lambda smaller so that C is greater than pi, which we can always do. Okay, so we now have a condition where our comparison function is assured of having an initial condition which is always greater than pi, which is always greater than the initial condition of the function we're comparing it with, because we know that theta 0 is chosen to lie in 0 and pi. And then since we know that theta tilde prime is less than the comparison function's derivative on 0 x1, by a comparison theorem, theta tilde is less than the comparison function. So in other words, theta lies beneath the line over here that goes to epsilon at x1. Okay, so theta is forced to be less than epsilon at x1 by the fact that we've chosen lambda to be large enough that the gradient over here, the gradient over there becomes very, very negative. Okay, and since it holds for any epsilon small enough, we have that this thing holds. Okay, so we basically force theta to be less than epsilon, and we can choose epsilon small enough, and this happens before x1. So if you go past x1, you still have the same gradient, you're still being suppressed to 0 very, very rapidly, but you don't have the risk of getting anywhere near theta or anywhere near pi, which we had initially. So then it's just 0. Okay, so just written out, basically you can always choose a comparison line with a large enough negative slope so that gets even larger as lambda goes to infinity, that theta tilde becomes arbitrarily close to 0 almost instantaneously. So you have these very sort of steep comparison lines that forces the thing to 0 and helps you prove the theorem. Okay, but intuitive, you can just see it on the picture of on the next slide or the previous slide. And that's enough. So now let's look at the Sturm Liouville theorem. If you remember in lecture 23 when I introduced it, I had the two initial conditions of the Sturm Liouville theorem when I summarized the main results, and what we're going to do is basically prove those two things on the slide. Okay, so the Sturm Liouville theorem is the boundary value problem, which consists of that eigenvalue problem as long as the boundary conditions specified at 2 points has an infinite sequence of eigenvalues okay, lambda n, which I just denote this way from 0 to infinity, that are ordered. Lambda n is less than lambda n plus 1, okay, and lambda n approaches infinity as n approaches infinity, okay, and the eigenfunctions yn associated with lambda n has precisely n zeros in the open interval AB. Okay, so this is the Sturm Liouville theorem. So we have had, in the previous two lectures, we have a lot of lemmas that gets us here, and now we're finally going to get to prove it. Okay, and I just want to put this picture up from a Matei's equation that we solved. Here we were just worried about, we just specified the initial condition and specified how lambda varied. Okay, and now we're going to show we can actually choose lambda for a particular constant so that the conditions of the theorem holds. Okay, so basically the boundary condition at x equals to a is satisfied by the initial condition. Tan of theta 0 is equals to alpha 2 over alpha 1 pa. Okay, so this point is sorted. Okay, but what is needed to find is a solution such that theta tilde at b, in other words, along this line for the Matei's equation, is equals to theta b, which is specified by the boundary conditions, okay, plus n pi for any integer from 0 to infinity. Okay, so theta b satisfies this condition, which is basically just saying that tan theta b ensures that relations between y and y prime at, and this should be pb, sorry, there's a mistake, are satisfied. Okay, now the way the proof goes is we can always solve this equation provided you get the correct one with b over there, and you can always find a theta b in 0 pi that satisfies this boundary condition, because tan, the inverse of tan, basically can take any value from minus infinity to infinity. Okay, so we know theta b exists, and the question becomes, can you find lambda so that once you've solved theta tilde over this whole domain, given the initial condition at a, that the lambda, for a particular lambda, that theta is actually equals to theta b. So suppose the theta b you chose was there, then the lambda that gave it to you would be lambda equals to 0.05. Okay, and the answer is yes, and the reason being is S1, basically, that we proved in the at the beginning of this part, is that theta tilde of b lambda, it's just applied at the specific point b, is a continuous monotonically increasing function of lambda. So basically, as you increase lambda, this makes like the fan. And we showed that that this continuously monotonically increasing function of lambda includes 0, basically goes from 0 to infinity by S1, right? In S3, we basically showed that lambda, as lambda approaches minus infinity or infinity, theta b lambda approaches 0 if lambda is minus infinity, and then moves up all the way to infinity, okay, so respectively. Okay, so there does exist over here, so pick any point along this little segment, because we want a theta b lambda in sort of in the region that's equals to theta b, and we know theta b lies between 0 and pi. So pick any point along here, begin with lambda equals to minus infinity, so begin down here, increase it until you eventually get to your point, and that's the prescribed one, and we're going to call that point lambda 0. Okay, so you can always do it. And the moment you've got that that value of lambda 0, you can solve for your whole solution, because you can solve r of x lambda 0, because you know what theta of x lambda 0 is. And once you have that, you can then construct y0, which is your eigenfunction of r, which is just r tilde x lambda 0 cos of theta tilde x lambda 0. Okay, The only thing which I've said here, but I'll get back to it in the second part, is it's not fully determined, because the differential equation for r is basically r prime over r equals to some function of x. It's basically determined up to a scaling constant. Okay, so you can rescale the solution. But we'll discuss how to fix that in the part B. Okay, so, and that gives you, so up to a scaling constant, you can basically define your function y0. Okay, and you can do the same thing for, suppose you want to find lambda 1. In other words, you want to find a solution that theta b plus lambda, say suppose up there, the y that gives it, you can always do it by S1 and S3. You basically then take lambda, you increase it so that this theta sweeps past particular value you want at theta b plus pi, so some place over there. You can find your lambda 1 that gives it. You can basically solve for the eigenvalue using the same process. And what you do know is, because that's in a way we explored the zeros in S1, basically, because y1 has a single zero, you can basically say, because your initial condition is 0, or in this region, and your solution is a greater than pi, okay, between 2 pi and pi, y1 has a single zero, x1 in AB, okay, where theta tilde x lambda 1 is equals to pi. Okay, and you can go on and do it for all n, and exactly the same arguments. You can show that theta n, you can always find lambda n, so that theta b lambda n is equals to theta b, the boundary condition, plus n pi. And the eigenfunction yn has n zeros, okay, in this region. And you can see that happen. So suppose here is an example of a lambda 1. Suppose we go up here where we can get, say, a lambda n, right? So we know that it's basically solving theta b plus 2 pi, and we know as a result it has 1 0 there and another 0 over there, so it has 2 zeros, and it's unique. Okay, so that is true now for all the roots. So there's a whole series of functions associated with the eigenvalue problem, the boundary value problem, that you can construct in this fashion, each time increasing the number of zeros that you get from the theta function, and increasing the eigenvalue. So it's kind of nice to argue this simply from the properties of the Prefer equation theta without actually knowing the details of p, the functions p and q and w. Okay, so that basically concludes the first part of this lecture, and we'll be looking at expansions on the eigenfunction basis for the second part.